In this video, I want to present the solar cell model and explain why do we have two currents associated with this particular model. In fact, we have a current that's called a diffusion current, and we have another current that's called a drift current. And I want to go more into why do these two currents exist. And I should mention that this is an extension of previous videos on the p-n junction diode. So if you have difficulty with this video, go to ewebpal.org and review those previous p-n junction diode videos. So here I have a simplified model for the solar cell shown in white. And in yellow, we have a load resistor across the solar cell. So this model has been simplified. I've eliminated some of the parasitic resistors associated with this model. And in fact, let's simplify things even more, and let's remove this load resistor, R. Now, how this model works is we have light that hits this diode, and the light generates this current in this current source here. Now with no load, this current is going to flow through this diode. So look at this. We have a current in this direction associated with this current source caused by the photons hitting the solar cell, but we also have a current flowing this way in the diode. So why do we have two currents associated with this diode? We just have one diode, but two currents. So what's going on here? So let's investigate this a little more. Here I have a p-n junction diode. And this diode has no load and it has no light shining on it. And what happens here is I get two currents. I get a current in this direction that's called a diffusion current. And at the same time, I get a current flowing in this direction that's called a drift current. So let's consider how this could possibly happen. Now recall that this P material has extra holes that I'll show by these X's. And recall that the N material has extra electrons, and those I'll show by these diagonal lines. Now since we have a higher concentration of holes in this P region, some of these holes can diffuse. And they diffuse because of a concentration difference. And some of these holes will diffuse into this depletion region, leaving positive, making this region more positive. And now this movement of holes, anytime you have charge moving, you have current. That's what current is, the movement of charge. So you can see that this hole moving down has caused a diffusion current. In a similar way, an electron here can diffuse into this region, making this region more negative. And again, an electron moving up is equivalent to a positive current moving down. So again, this electron causes a diffusion current. But there's also a drift current. Let's consider how that could happen. Now, as this diffusion process continues, we get positive charge at this surface, and we get a negative charge up here at this surface. And that causes an electric field that points in this direction. Now that electric field is going to repel these holes from diffusing over. And in a similar way, they're going to repel these electrons from diffusing into this depletion region. So they tend to block the diffusion current. But this electric field causes a drift current. Now, how could that possibly happen? Well, let's consider that there's a certain amount of minority carriers. There are some holes in this N region. Now, due to thermal vibrations and movement, some of these holes can wander into this region. If that happens, this hole becomes current that is pushed by this electric field. This electric field will push the hole into this region. And that causes a current in this direction. And a current caused by this electric field is a drift current. Now, in this region, we can have a minority of electrons. If an electron comes into this depletion region, it's going to go in this direction, caused by the electric field. So that can be thought of, again, as a positive current flowing in this direction. So that adds to the drift current. And if we have no load, no light, we have a diffusion current flowing down and a drift current flowing up. And these currents balance each other and they cancel each other out. Now, you can have, as we get more holes in this region, some of these holes can, due to vibration, can actually have enough energy to overcome the electric field, and that causes diffusion current. And some of these majority electrons in the N region have enough energy to overcome this electric field, and they can cause diffusion current. So the diffusion current has to overcome this electric field barrier due to the concentration. And the drift current is caused by this electric field. So let's consider this when we have light shining. Let me erase some of this stuff. Now let's consider what happens in the case where we have this PN junction diode and we shine light on it. So let's say that we shine light into this N region, and as a result of that light, we dislodge an electron from the lattice. So we have an electron here, and because the electron has been moved from the lattice, we have a positive charge associated where that electron used to be. So the light shining has created an electron hole pair. So the light has increased the mobile charge carriers in this N region, and in a similar way, if the light hits the P region, it does the same thing. It produces extra holes and extra electrons. Now recall that we have an E field in this depletion region that points in this direction. Now let's say that this hole that was generated by the light wanders over into this depletion region. It feels this electric field and is propelled in this direction. So it causes a current in this direction. That's a diffusion current, or excuse me, a drift current. The drift current is caused by the electric field. Now this electron, if it wanders over into this region, it's going to be pushed away. But if this electron up here wanders into this region, it's going to feel this electric field and it's going to cross this region. So this electron moving in this direction is like a positive current moving upwards. So what happens when light shines on this PN junction diode, we get more drift current. But this drift current tends to build up the holes on this side, which makes this side more positive, and this side more negative. Now when this happens, we get more positive charge here. And some of this positive charge will have enough energy to overcome this electric field and become current in this direction, become diffusion current. And so what happens as we shine light on this PN junction diode, we get increased drift current caused by this electric field, and that builds up charge. So we build up more negative charge here, more positive charge here. So we have more charge bumping into each other, and some of that charge can overcome this electric field and become diffusion current. So as we shine light, we increase the drift current and we increase the diffusion current, and they exactly balance each other. Since we have no load, these currents cancel each other out. Now let's consider what happens when we have this PN junction diode and we put a load resistor across it and we shine light on it. Now recall that we have an electric field in this depletion region that points in this direction. Now in the case where we had no load that we just talked about, we're operating at this point on the current versus voltage curve for the solar cell. And in this case, the resistance R is equal to infinity. And what happens then is that the light shines on this diode. It produces electron and hole pairs in the N region and in the P region. And this electric field causes positive charge to be built up on the P region and negative charge to be built up in the N region. And with infinite resistor, we have the charge just builds up and we get more charge in this region that, due to the higher concentration, causes diffusion current in the opposite direction. So we end up with two currents. We end up with drift current caused by the electric field and diffusion current caused by the concentration differences. Now, if we put a short circuit across here, we're saying that the resistance is equal to 0. And then as we add load to the circuit, this positive charge can now flow through this load to this terminal. It's a little bit like having a battery. This terminal is charged positive, this terminal is charged negative. We put a load on it and we can do useful work. So what happens is that the current in this direction, the drift current, can now flow through this load. And the drift current can dominate the circuit. And the characteristics for this solar cell, in this region, the solar cell acts more like a current source. And in this region, the solar cell acts more like a voltage source. Now, if this curve were flat here and very steep here, we'd have a perfect voltage source here and a perfect current source here. And so with this load, we can do useful work. We want to operate at a point here where we maximize the current times voltage and we extract the most power from the solar cell. So hopefully this video gives you some idea of how this solar model works and why we have two currents, one caused by a concentration difference and the other caused by the electric field.